This is Cole Miller, a bridge engineer from HDR. Doing a lot of Julia work.
All right, Handcalcs, calculations you can read and reuse. First off, I just want to say thank you to all those who helped me bring this package to life. A few names who helped me on the various Julia community channels are listed: Adrian Bramer, Matt Bauman, and Mose Giordano were some who consistently helped me with the questions I posted, and I don't know if I would have figured things out without them. Connor Forster is another I would like to thank. I took his Python course for structural engineers, and I would recommend it to any structural engineer who would like to learn Python. He's also the creator of Handcalcs.jl, which is an amazing Python package, and this package is an implementation of that package for Julia. I also want to thank the creator and maintainers of LaTexify.jl. Handcalcs under the hood just calls LaTexify, and it does all the heavy lifting. Lastly, I want to thank Tim Holy for creating code tracking and revise. These packages provided the tooling for what I think is the most valuable part of Handcalcs, which we'll get to later. So a little bit about me. I'm a bridge engineer in Dallas, Texas. I was first introduced to programming in college through MATLAB, and I quickly found I really enjoyed programming. Now I code somewhat regularly, mostly use VBA and Python. But my favorite language is Julia, and I've been using it in my free time for the past year and a half, and I hope to use it in industry. And I think this package could provide a valuable reason to do that. So I wanted to show it to you today. So a big part of being a structural engineer is documenting our calculations so someone can verify our work. I wanted to show you some of our current tools for doing that. Our main tool is Excel for documented calculations. I personally love Excel, and combined with VBA, it can be a very powerful tool. I think Excel's greatest strengths are that it's fast, it's easy to use, everyone knows how to use it, you can change it easily, and its reactivity is unmatched. The actual cells, though, doing the computation don't actually show the work being done, so we typically have to manually add in a cell to the right, documenting what the cell did. You can see an example of that in the image shown. The cell highlighted in blue is showing what the cell to the left is computing. It can be a little complicated to read for some of those longer formulas. Another tool that is used by structural engineers is Mathcad, and for some this is preferred over Excel. I think for some it provides a more readable calculation as well as including units with proper unit conversions. So it's a nice tool. And you can see an example of that in the image shown. And so here's a little snippet of what Handcalcs can generate when working through Quarto. And the question is, can Handcalcs become a useful tool when creating documented calculations? And I'm hopeful, but I think there's still some pieces needed for a better user experience. So here's kind of just a summary of what I think, how they rank against each other. And I would say in terms of readability, reusability, version control, and testing, Handcalcs is like really good, and the areas of improvements would be like ease of use and reactability. So now for the demo of Handcalcs. After installing Handcalcs as you would any other Julia package, all you need to do is call these two packages to gain full functionality. Most of you likely have revise in your startup.jl file, so all you really need to do is call using Handcalcs. So Handcalcs exports two macros where all the functionality stems from, Handcalc and Handcalcs. Think of Handcalcs as doing, or Handcalc as doing a single inline LaTeX expression, and Handcalcs as a multi-line equation. I recommend using Handcalcs. It inlines into Markdown, handles multiple expressions, and cleans up equations of redundant information. So here's a single expression example. Let's try to calculate the area of a circle. So the first line here, I'm just setting the variable d equal to 5, and that'd be like the diameter. And then in this next line, it's basically the equation of a circle, and all you have to do is put Handcalcs in front of it, and Handcalcs will render the equation shown. So Handcalcs was able to show the equation defining area as a LaTeX expression, showing both the symbolic and the numeric parts. And yes, the variable area was also evaluated. So the number of decimals in that above expression may be too much, so we can change that. We can use the set Handcalcs function and set the precision equal to 2. And now running that same line there, you can see now it's reduced the number of numbers after the decimal. So here's a multiple expression example. So here I'm just setting variables b and h equal to 5 and 15. When you have a multiple expression example, you want to wrap your equations in a begin and end block. So here I just have equations for ix and iy, and if we run that, you can see Handcalcs is able to render both equations nicely. And yes, iy and ix are evaluated. You can also use strings to add comments to the equation. So here's just that same ix equation, and I've added in a string on the side there, and you can see that. And now Handcalcs will render that string in parentheses to the right. Using semicolons are nice, so you can see, you can make the code more readable. In reality, it's just this. This is equivalent, and you can see it renders the same thing. So working with known variables, say we previously defined variables, assume these are constants, inputs, or previously calculated variables, we can render those out nicely. So recall the ix and iy variables we created. And then here in this last line, you can see I've specified columns is equal to 2, or calls is equal to 2, and color is equal to blue. Calls is equal to 2 is going to split the equations into 2 columns, and color will change the text to blue. And you can see that there. So when the equations are too long to fit on a page, you can use the length is equal to long. So here I just have some variables I'm defining A, B, and C. And in the Handcalcs block, I've got just the quadratic formula. And then at the last line there, I've got length is equal to long. And you can see Handcalcs renders it in multiple lines. So you can change the default settings similar to LaTeXify. Handcalcs has a way to change some default settings using the set Handcalcs function. A number of these we've covered. Most of these you can use at the end of the Handcalcs macro, as I've shown previously. And the set Handcalcs function just allows you to set these as defaults instead of having to change the setting every time you use the macro. So we've gone through columns, SPA spacing, change the vertical line spacing between expressions. Length we covered, color, changing the color of the output. HM, this is for people familiar with LaTeX. You can change the environment from aligned, which is the default, to like align or other LaTeX options. HRender we'll cover in a little bit here. You can choose between equation, symbolic, numeric, and both. Precision, we saw an example of that. Changes the default number of decimals, or numbered after the decimal that are rendered. And not funcs, parse pipe, parse ifs we'll get to later. And disable is just, you can disable Handcalcs, and everything that's in the Handcalcs block will just run as if it weren't in the Handcalcs macro. So setting the rendering format, like Handcalcs provides a setting to change to a different rendering format. The choices are between equation, symbolic, numeric, or both. And so this is an example of the equation rendering. So you can use the set Handcalcs function and set the hrender to equation. And when you run this here, you'll see it just shows the equation and not the actual result. But IX is still evaluated. Symbolic, you can use the hrender again to switch to symbolic, and that same equation, you can see it just shows the symbolic parts. And then numeric, similarly, it'll show the numeric parts. So this is really meant to be a setting overall, but you can use the set Handcalcs function to turn the setting on, and then use it again afterward to turn it back to the default. So this package integrates with Unitful and Unitful LaTeXify. If you're going to use Unitful, recommend using Unitful LaTeXify as well. So an example of this, if I have A and B and I set them to 2 inches and -5 inches and run an equation, Handcalcs will render the units inside of the equation, which is nice. And so you can use the pipe to convert output to a specified unit, just like you can in Unitful. And so an example of that, like let's say I had B is equal to 40 feet, T is equal to 8.5 inches. That equation A is equal to B times T. Unitful wouldn't promote that to a default unit, so you'd have feet inches. And you can use the pipe operator to change it to inches squared, and Handcalcs will run that, and it will convert the output to inches squared. And you don't see all the, the pipe in the equation, which is nice. So the best part, function unrolling, the Handcalcs macro will automatically try to unroll the expressions within a function. The expressions must have the following pattern. So a variable equal to a function call. This is recursive, so if you have functions that call other functions, it will continue to step into each function to unroll all the expressions. One issue that can arise for the functions that you do not want to unroll, consider the expression y is equal to sine of x or y is equal to x plus 5. Both of these expressions match the format variable is equal to a function call. And so they would therefore be unrolled. This would result in an error since these functions don't have generic math expressions that can be LaTexified. So you'll need to use the notfuncs keyword to manually tell the Handcalcs macro to pass over these functions. And some of the common math functions that you will not want to unroll are automatically passed over. So here's an example of that. There's a function that's defined in the test Handcalcs function package called calc.ix. The definition looks like the following. It's basically the ix equation that you had seen previously. So if we try and call that function with our Handcalcs macro, we'll bring in the test Handcalc functions package. We'll set b and h equal to 5 and 15 like before, and then we'll call that function with that similar variable equals function call. And you can see when Handcalcs renders that, it actually finds the function, steps into the function, and pulls out the relevant equations in that function. So the ix variable is evaluated, ix being the variable assigned in the Handcalcs part. Variables within the actual function are not defined in the global namespace. And I guess there's a caveat. Return statements are filtered out of the function body, so keep relevant parts separate from return statements. So here's an example of a recursive unrolling example. There's a function defined in the test Handcalcs function package called calc_eyes, and you can see calc_eyes calls calc_ix, and it also calls calc_iy. So if we try to call that, you can see the format there. It actually returns 2 variables, ix and iy, and you can see I'm pulling that out, ix and iy, in the Handcalcs body, and Handcalcs is able to take care of that. And so when this runs, Handcalcs is able to find both of those equations within those functions. So it's recursive. So debugging function unrolling, if you encounter an error, you can use the showfuncs keyword. This will print out all the functions Handcalcs stepped into. So for example, this same function call that we did just before, if you add the showfuncs is equal to true there, Handcalcs will just print out each function it stepped into. There was no error here, but you can see the Handcalcs stepped into all 3 functions. So unwanted function unrolling, so let's try to call sine and cosine. So I'm just going to set x is equal to 0. And then, so since we don't want to unroll sine and cosine, we'll specify notfuncs is equal to sine and cosine. And so Handcalcs will see this format, and it'll see that it's in the list of notfuncs, so it'll pass over it, as well as the cosine one. So then you'll see that it just calls the function call in there like you would want. So stepping over functions, so there's a default list of current functions that Handcalcs macro steps over. Here they are, and they're listed in the documentation. And if you want to add functions to your specific project, you can use the set Handcalcs function and use the notfuncs keyword. Working with structs, so if you have functions, so I guess here's a side note, if you have functions that are outside of a package, you'll need to use the includeEt function from revise, as well as wrap the code in a module. So if they're not actually in a package, you'll have to follow these steps. So here I've wrapped the file in a module, and then here's just a simple struct, a rectangle struct with a length and a width, and then I've got the calc area for that rectangle struct and a calc perimeter. So if I were to bring this in, I would need to use that includeEt function and revise. And then in line 4, you can see I'm just initializing that rectangle struct. So if you recall that calc area function, let's see if we can call that. And then here's the line, Handcalcs area is equal to calc area. And then I've got the rec variable in there. And you can see Handcalcs is able to step into that and pull out the equations. So you can avoid that object.variable syntax by using the struct unpacking Julia syntax sugar. So like for this calc perimeter example, I've got the unpacking syntax sugar there in the function definition. So I'm pulling out the length and the width like directly. And so you can kind of get by with that object.variable syntax. So if I call that, you can see Handcalcs is able to step in and render that function, or that equation. So if statements have two different formats. The default format we'll show here. So this is like a simple if statement, x is equal to 1. Since x is less than 5, we're going to be in that else branch. So Handcalcs will render that, and you'll see that since line, since x is greater than 5, that's false. We're just showing that x equals 10 branch. And then the other option would be the LaTexify format. And so here's the same if statement, and you can just you can specify it with that parse ifs is equal to false, and you'll go back to the LaTexify format, and you can see how it shows it there. It shows both branches. So the benefit of using the default format is it works with function unrolling. So here's an example of that. I've got b is equal to 1. Since b is less than 5, we're going to be in the else branch. I'm calling that calcix function. And when Handcalcs renders that out, you can see that calcix function has been unrolled. Whereas LaTexify format won't function unroll. And so you'll see just the function call itself. So writing packages, Handcalcs was built with the intent to build packages with it. These packages do not need any dependency on Handcalcs. So I just wanted to give a demo of this package I've been writing. AISC Steel is a package that was built as a tool for structural engineers. It has also been the package that I use to test the limits of Handcalcs. It covers the steel reference manual that engineers use to design steel structures. Here's just like a little snip of the manual. The manual is just full of mathematical equations with a reference to those. And I've just implemented those in this AISC Steel package. So let's go through a basic calc that we would do using this package. We will use Handcalcs to generate and display the equations. It's important to note that the AISC Steel package doesn't know about Handcalcs. AISC Steel has no dependency or extension for Handcalcs, but Handcalcs is able to render out the functions inside Handcalcs. For the example, we will go through calculating the bending strength of an I-shaped member. You can see an image of the shape there in the lower left. It looks like an I. The image of the lower right shows what we would be after. What is the max load P that the eye shape could take? So just like, I guess, some basic information of this calc, there's basic failure modes of an eye shape that you'll have to watch out for when checking bending. The upper left is the failure mode that will occur if the other three do not. This is the theoretical maximum strength of the section. Then you have the flange buckling and the web buckling failure modes. Basically, if your flange or web is too thin, then your flange or web will buckle before you ever reach the first failure mode. So we classify the flanges and the webs first to see if there will be an issue. And then the last failure mode, the sketch in the lower left, is dependent on the unbraced length of the member. This is called lateral torsional buckling. Basically, if the distance between braces is too long, then the entire beam will want to buckle sideways and start to twist. So depending on the slenderness of the flanges and the webs and the distance between the brace points, the eye shape will be governed by different equations. And now we'll show how to use Handcalcs to only show the relevant equations. And we can use it to generate a nice report. So first, I'm just importing AISC steel in the various submodules. This phi B is just like a reduction in the overall capacity. Typically just take 10% off as a safety measure. And then this line, I'm just initializing the W shape. This is a W10 by 12. It's basically just looking through a database and pulling in a bunch of parameters. And then LB is just the length of the beam in our case, and that's 10 feet. So we can pull out the parameters of the W shape with the unpacking syntax in Julia, and then we could show those in Handcalcs, just putting those in the Handcalcs block. And you can see I've got columns is equal to 4, colors is equal to blue, and that renders out nicely. And then first we want to check the flanges and the web. And so this function call is just a function to check those flanges. And you can see just it's pulling out multiple variables, and Handcalcs is able to handle that. And you can see it unrolls all of the equations in that function. In this case, the flange is non-compact, so since it's not compact, we'll have to check that flange buckling in our case. Checking the web, it's similar. So if we just run that, we'll see the web is compact, and since the flange is non-compact and the web is compact, we're in the criteria called F3. So there's a lot of code here, but the first one is basically just the call to the first two functions that I showed, and it's going to spit out F2 or F3. And then, so I've got this if statement showing if it's F2, I want to do this. If it's F3, I want to do this. And then looking at this part 1 heading and part 2 heading, this is pretty neat because you can dynamically change the titles of your sections. And so you can see F2 versus F3, they're different titles. And then lastly, in the Handcalcs part, this will be the relevant equations that are rendered out instead of the F2. So running this, you can see it rendered that out, and it rendered out all of the equations there. And then next, we need to calculate the lateral torsional buckling. Here's just kind of an image of what that looks like. This would be a real-world example of what that would look like. So we want to avoid anything like that. And so here I'm just putting part 1 heading and just outputting that. So we get a nice title, dynamic title. And then this part 1 check, I'm not in F2, I'm in F3. So this part will be the thing that renders out. And you can see that there. Next would be compression flange local buckling. And you can see the failure mode there in the image. And then this would be like a real world example. And so very similarly, part 2 heading, it's nice and dynamic. And then I'm going to show the relevant equation for F3. And you can see that there. And then lastly, for F2 or F3, I'm going to pull the minimum of those two values, and those render out. So there is a function that does the whole calc, and that's the calc MNX, and you could use that to be like as a check. I guess you could use Handcalcs to render that whole calc, just using the one that does the whole thing, but it wouldn't be best for like a report. But it is great if you want to run it and just have a deeper understanding of the calc, and you can see that it runs all of what we showed earlier. And lastly, calculating the max load P. Now that we know our capacity, we can calculate P, which is about 8 kips, which is about 8,000 pounds. So reporting this entire document was created with Quarto and Quarto Notebook Runner, and you can use it to create professional looking reports like so. And that's just an example of the report. Thank you.
All right, thanks, Cole. Are there any questions? There's one in the back. I'm first. Oh, there's a lot of here. I'll go back there because I saw it here.
Hi, just a quick question. Do you think that using something like symbolics would help you to do the function tracing? Because it already has support for like registering functions, and a lot of things are already registered. And it is also compatible with LaTeXify.
Yeah, symbolics and how it doesn't work with Handcalcs. Yeah, just the way Handcalcs is the numeric substitution part, it actually needs that value of A. And when you set the symbolic A, now you can't have a numeric number there.
You can call substitute, and you can give it a dictionary, and it can do any substitutions you want.
You can call substitute, but I think still in main, like in the main global namespace, it's still a symbolic variable, symbolic struct. So the way Handcalcs works right now, it wouldn't work. So yeah.
Okay.
Maybe you can work on that more.
Yeah.
All right, there were some questions down here. Who would like to go next? Okay.
I was wondering how you capture basically the different operations when you unpack the functions, right? So in other words, if somebody wants to maybe only display a subset of the calculations in a function, how does that work?
So right now, what it's doing is, so code tracking will, if you supply the types, code tracking will give you the whole function body as a AST. And then I take that AST and I take out all of the equations. And then since I had to escape the macro to get the types,
yes,
I then have to use eval for the function unrolling part. But yeah, that's the basics of how it works. I basically pull that all into an AST, I run it, I wrap it in a let block so none of it, escapes to the global namespace, and so yeah.
Wonderful. I mean, as a structural engineer, super cool.
Hi, thanks. Two quick questions. Just to be sure, when you said the precision is only for the printing, right? Internally?
Yeah, only for the printing.
Okay.
Yeah.
And the second one is there any chance for this to work in terminals or only in graphical interfaces like Jupyter or something like that?
Journals, you said?
Text mode, terminals.
Oh, terminals. Yeah, so it outputs a LaTeX string, if you know that package, LaTeX strings. So that's what it outputs. There is a potential that you could have multiple backends. So right now it's LaTeXify, but I know there's a typst LaTeXify version maybe in the works, so you could maybe have a backend there. So yeah, there's potential for it, I guess. Yeah.
Thank you.
Okay, thanks again. Let's thank Cole one more time.